So we had shells, we had subshells, then we had orbitals where the electrons are basically, and then the number of electrons that we need to fill in over there. So shells, the first shell had one subshell, that was 1s. And how many orbitals should it have? Because 1s can only accommodate 2 electrons, one orbital, right? And we do know that according to the formula 2 n square, how many electrons are accommodated in first shell? One, because first it only has one orbital, and secondly it only has one subshell, and that is an s subshell, which can maximum accommodate 2 electrons, right? So you have to be able to link each of these headings with each other. And then about the second shell could accommodate about 8 electrons, and for 8 electrons it needed two subshells. One s subshell was needed, and the other one was a 2p subshell that was needed. So s would accommodate 2 electrons. So in order to accommodate 2 electrons, s has one orbital to contribute, and p can accommodate 6 electrons. So in order to accommodate 6 electrons, how many orbitals would p give? 3 orbitals, right? And so on, like we discussed yesterday. The third shell would have to accommodate 18 electrons, and to fill in 18 electrons it needs 3 subshells, and each subshell has a set number of orbitals in which it can accommodate those electrons, right? So d, now we'll just do it right here. How many orbitals does s need in order to fill in these 2 electrons? It has one orbital, right? And what about p? It has 3 orbitals, d has 5 different orbitals, and f has a total of 7 orbitals to accommodate these 14 electrons. Okay, now let's continue from here. Now, the analogy I gave you in your demo class also was that you have to think of it like a city in which you have a street, in which you have a house, and inside the house you have people. Okay, so the city is basically a shell. Inside the shell you have street, that means subshell, and then inside the subshell you have a house, which is the orbital where people live, which means the electrons, right? So these things are, it's just to memorize and understand that there is levels to it. Okay, so let's draw a diagram to visualize basically these shells. So if I draw the diagram of atomic structure right here for A levels, let me just copy the one which we made above, right? This one. Let's just copy this diagram and zoom in. This diagram right here, I'm going to zoom in this part, this one right here. I'm going to zoom in this part. Okay, so let's zoom in. So you first have your nucleus over here, this ball-like structure, and then after the nucleus over here you have the first shell. So I'm going to draw the first shell. This is your first shell, right? After the first shell you have your second shell right here, and the third shell, and then fourth shell. We have zoomed in into this piece which I just highlighted. Okay, so we have this second shell right here, then you have this third shell right here, and then you have this fourth shell right here. So first shell, second shell, third shell, and this is the fourth shell. Now inside these shells, what do we find inside the shells? We find subshells. So in the first shell, how many subshells does the first shell have? There's only one subshell, which we call 1s, right? And it is closest to the nucleus because it is in the first shell and it is the subshell of the first shell. Yeah, I can hear you now. Okay, I'll repeat it from there. So this is the nucleus. I'm going to zoom in into this part which I highlighted, okay, for the atomic structure. Now this is our nucleus. We start from here, right here. We're starting from here. Then there comes the first shell, which I do like this with the brackets, right, and with the curly brackets basically. Then you start off with the second shell, then that ends, and then you move on to the third shell, and then that ends, and then you move on to the fourth shell. Now we're talking about the subshells. After shells, what do you see after shells when you magnify? You see subshells. So now you're going to draw subshells in the magnified part. So in the first shell, which subshell is present? Only one subshell, which is 1s, right? In the second shell, how many subshells do you find? Two subshells. There's there's 2s, and then there's 2p. Can you hear me now? Yeah. So there's 2s and then there's 2p. And what about the third shell? How many subshells in the third shell? There's three subshells. There's 3s, there is 3p, and then you have 3d. And what about the fourth shell? You have 4s, 4p, 4d, and then you have 4f. Now inside these subshells, because we have magnified the atomic structure, we have magnified the part I just highlighted. Inside these subshells, you find what? You find orbitals. So the 1s subshell has one orbital. Let me change my color. Yeah. So it has one orbital. This is the one orbital that it has. Then the 2s, what about the 2s? How many orbitals? One orbital. What about the 2p? How many orbitals does the p subshell have? Three, yeah. So 1, 2, and 3. What about 3s? One orbital. 3p, 1, 2, and 3. And what about 3d? It can accommodate 10 electrons, so 5 orbitals. 1, 2, 3, 4, and 5. Then we move on to 4s, which has one orbital, 4p, which has 3 orbitals, 4d, which has 5 orbitals, and then 4f, which has 7 orbitals. 4, 5, 6, and 7. Right? So we have just zoomed in into that part. Now inside these orbitals, what will you find? You will find the electrons. So 1s would have 2 electrons in its only orbital. 2s would have 2 electrons in its only orbital, and 2p has 3 orbitals, so it would have a total of 6 electrons, but 2 electrons in each orbital, because one orbital can only take in 2 electrons, right? And then same goes for all the other orbitals. You just fill them up. Let's just fill these. Now first thing to remember is that whenever you have to fill electrons, this is a rule, by the way, we will study this rule after a few more topics, but in electronic configuration basically. So there's a rule first that any subshell or any shell which is closest to the nucleus, it is more stable. We used to call shells energy levels as well, right? We used to call shells energy levels. Why? Because the further away you are from the nucleus, the more energy you have, the more unstable you are, right? So 1s was closest to the nucleus. So if I plot energy right here on the left hand side, the energy would increase as I move away from the nucleus. Okay, so 1s closest to the nucleus has the lowest energy level. Then after 1s, the second shell starts. So 2s has the second lowest energy level, but after 2s, there's 2p. Now now comparing 2s and 2p, who is further from the nucleus? 2p or 2s? 2p is further away from the nucleus, right? So 2p has 3 orbitals which are further away from 2s, hence they have greater distance from the nucleus, so they are a little more unstable compared to 2s orbital, right? And as you move along, you will have more and more energy for each orbital. So if I just ask you from this diagram, which orbital is at the highest energy? Yep, because it has the maximum distance from the nucleus, so it has had a very large energy, right? And even when we're filling electrons, we always fill which orbitals first. Electrons want a stable place to stay. Okay, so which orbitals do we fill first, which are closer to the nucleus? This is a rule for electronic configuration. Okay, so just remember that for now. Let's move on to another thing, that is shapes of orbitals for now. Let's move on to shapes of orbitals. There are two orbitals whose shapes you need to know for your exam in AS, and the rest of the orbitals are for A2. Okay, so you have an S orbital. Now remember, an orbital is basically a region where the electron density is maximum, or the probability to finding the electron is maximum, right? It spends its most time, or the maximum amount of its time around that region. Okay, so for the S orbital, you'll just memorize the shapes, but for now, the S orbital, around the nucleus, the S orbital is a space which looks like this, in which electron spends most of the time like this, in a spherical basically region. This is the shape of the S orbital. So if I just outline the shape, it looks a bit like this. This is not a circle, by the way. This is a sphere. Okay, it's a 3D ball-like structure. Okay, so the electron will spend most of its time in an S orbital, which looks like a 3D ball-like structure, right? So if I just draw the axis, this is the x-axis, this is the y-axis, and then there's this 3D axis, which is away from you and towards you. This is the z-axis. And if we say that the intersection point of all these axes is basically the nucleus in the middle, that's the nucleus in the middle right here, then the s orbital around the nucleus is a region which looks like a sphere, right? So this is our sphere. So I would call this 1s. But what about the 2s? 2s has the same shape, but it is away from the nucleus, so it has a larger size than 1s. Okay, so exactly same structure for the 2s orbital in the 3D axis. This would be the nucleus right here, and the 2s would have a larger spherical size because it is further away from 1s. It comes after 1s, so it has a larger size than 1s. Okay, so basically again, this is the nucleus right here, and the electron would spend most of its time in this region. That's why we call this 2s, and it is again spherical in shape, right? But you have to remember that 1s is smaller than 2s, and 2s is smaller than 3s, because 3s would be in the third shell. And in order to like cover all the subshells before it, it has to be larger than all of them, right? So this is our 2s subshell. This is 2s. It is larger in size. Shape is same, but it is larger. So the s orbital is spherical in shape. All right. Let's just color it like this, so you know that this is not a circle, it's a sphere. Now let's move on to the p orbital. Now in terms of the p orbital, so the first p orbital that we encounter while filling electrons is the 2p orbital. Before that, there is no p orbital. There's only one s, 2s, then there's a p orbital. So the p orbital, so the p subshell basically has three orbitals. What's the shape of these orbitals? First, I'll draw them and then we'll discuss. So basically, again, we have to draw the axes. So this is our axis. This is the x, this is y, and this is z. Now, in p orbitals, you have three orbitals, right? P has a capacity of 6 electrons, so it needs three orbitals to accommodate those 6 electrons. But what's the shape of the p orbital? Now, in the p orbital, the electron spends most of its time like this around the nucleus. This is the nucleus. This is the p orbital, the region where the electron is going to spend most of its time. So if we just outline this shape, how does it look? If you just outline this shape, we change the color. It should look like this. This is the region where electron spent most of its time, or this is the region where the electron spent most of its time. What do you call this kind of shape? It's basically two balloons which you have like attached from the tail. What do you call this kind of shape? Do you go to the gym? Like a dumbbell shape? Yep, it's a dumbbell, right? So you call this a dumbbell shape. So dumbbell shaped. So that's the shape of the p orbital. Again, you do not have this outline around the p orbital. You're just making this outline to basically understand the shape of the p orbital. Okay, just like we did for the s orbital. It's basically this is the region in the p orbital where the electron will spend most of its time. But you said you had three orbitals. This is only one orbital from the p subshell. All the other orbitals will also have the same shape, but they will have different orientation. So the three p orbitals, they're basically divided. They all have the same energy. Remember this diagram right here? This is the first p orbital, this is the second p orbital, and this is the third p orbital, right? All of them on the y-axis have the same energy. Are they at the same energy level? Yes. Yes. But are they at a different energy level compared to the 2s orbital? Yeah, they have greater energy than the 2s orbital, but all these three p orbitals are at the same energy with respect to each other. And you also call orbitals having same energy, orbitals having same energy as degenerate orbitals. We call orbitals which have same energy as degenerate orbitals. Okay, so let's go back to drawing the structures. So the next axis I'm going to draw right here. We'll keep everything same. We'll just draw the next orbital. So this was the x-axis, this was the z-axis, and this was the y-axis. Now I'm going to be drawing the second p orbital. So we just do p in the x direction. So this would be px. What about the p in the y direction? Has the same shape, but it is along the y-axis. So basically, it would have a shape like this. A maximum electron density in this area along the y-axis. So if I outline this too, does it have the same shape? Does it have the same dumbbell shape but in the y-axis? Exactly, right? So this is the py orbital. So we have px, we have py, and now we're going to move on to pz. I'm just going to draw pz right here. It's in the 3D axis, but it is along the z axis. Okay, same shape, but it is 3D right now. So it will be like this. Let me just choose a color like that. Now, along the z-axis, so I'll draw it right here. Electron density would be in this region. Now forget the x and the y for a second and look at the z1. It's towards you and it's away from you, like this. So if I outline this too, then I'll get a dumbbell shape in the z-axis, right? So I have three p orbitals, and all those p orbitals have the same energy. The only difference between them is that they are arranged on different axes, right? So px, py, and pz. Now these are the only two orbitals that you need to know the shape of. Okay, you don't need to know the shape of the d orbital or any other orbital. Clear? Let's move on to exactly, yeah. If this is 2p, 3p would be larger than this. Like for example, I'll draw it on the x-axis one. If you had 3p, I'll draw it with a highlighter. 3p would have been even larger than this, but it would still have a dumbbell shape. Okay, so 3p would be like this, dumbbell shape, and then 3py would be like this, and 3pz would be in the z-axis like this, but it would be larger than the 2p orbital. I hope I have that animation right now so I can show it to you. Do we have this? Let me check. Mm, no, it got removed from here. It's okay, we can look at it later. First, we need to understand one more thing. So, should we move on? Okay. So, now you need to start electronic configuration. So, first, you need to learn this, memorize this. What you need to memorize is that what's the order of the shells and the subshells, and how will you fill electrons. So in order to fill electrons, just memorize this diagram that we're going to draw with diagonal lines in it. Okay, so whatever comes first diagonally in this diagram, you will fill that subshell first or that orbital first. Okay, so whenever, just write this, whenever we write the electronic configuration, we will fill the electrons according to this diagram. So this diagram makes your life easy. You don't need to memorize anything anymore. So this is the nucleus. And what did we say earlier? What did we say? That we fill the subshells or those orbitals first, which are closer to the nucleus, right? So 1s was closest to the nucleus. This is the first shell. 1s is closest to the nucleus. Then you write 2s and 2s, and the second shell has 2s and 2p both. Then you have the third shell, which has 3s, 3p, and 3d. Then you have the fourth shell, which has 4s, 4p, 4d, and 4f. And then we'll continue with the fifth shell also. Then you have 5s, 5p, 5d, and 5f. And that's all you're going to need. Okay. The maximum you'll ever go to in A levels is 5s, and very rarely if you have to go to like 5p. Now, what we'll do is, in order to find the order in which the electrons are filled, or in order to be accurate with the filling of that orbital first, which is closest to the nucleus, you draw diagonal lines here. Okay, and those diagonal lines will basically help you find out which orbital is closer to the nucleus and which orbital I have to fill first. Okay, so now we'll draw diagonal lines. So in order to fill them in order, just draw diagonal lines starting from 1s. So first the electron goes into 1s. After 1s, the electrons will go into the 2s orbital. After 1s is completely filled, you move on to 2s, then you move on to 2p, and after 2p you're filling 3s, and then you move on, right? After 3s you go into 3p. That means 3p is further away from the nucleus compared to 3s. And then after 3p you go into 4s, not 3d. So what is this diagram telling you? Where is 4s? Is it closer to the nucleus than 3d? It is closer to the nucleus. Yep. Yeah. So 4s is closer to the nucleus compared to 4d, right? And we will explain that further later on. So after 4s you fill 3d, and then after 3d you fill 4p, and again 5s would be closer to the nucleus compared to 4d, right? So this is all you're going to need in order to fill in electrons. So just follow the diagram, memorize the diagram, and then you just make diagonal lines. Whenever you get stuck, you just make diagonal lines and then you revise it. But the number of times I'm going to make you write the electronic configuration, you're never going to make a mistake in it ever again. So let's write a bit like some points over here. So the first point is orbitals which are closer to the nucleus have what kind of energy? Yeah, nucleus are more stable, so low energy. So they have low energy. And the second point we could write from here is that as we move away from the nucleus, what happens to the energy of the orbitals of the subshell increases. As we move away from the nucleus, the energy of orbitals increases. So let's just write a dummy electronic configuration for any element which has X amount of electrons, right? So how would you fill electrons? This is known as the 1s notation. I'm just going to tell you about the 1s notation. This is how you write electronic configuration in A levels. 1s notation, in which basically you write the subshell and then you write the electrons in its exponent. This is known as the 1s notation. So now, right now, I don't know how many electrons are there. Just say there are infinite number of electrons. We have to start filling electrons. Where will the electrons go first? 1s. So we'll write 1s, 2. After 1s is filled, where will you go? After 1s, you move on to 2s. So we're at 2s. So 2s, maximum 2 electrons. After 2s is filled, you'll move on to 2p. So 2p, maximum 6 electrons. Now I'm assuming that it has infinite number of electrons, so we can use all of these orbitals right now. So after 2p, you move on to 3s. So it will be 3s2. Then after 3s, you move on to 3p. So it would be 3p6. And then you move on to 4s. It would be 4s1. Sorry, 4s2. Right? But you have to keep in mind that after 3p, you do not fill 3d because 3d is further away from the nucleus and 4s is closer. So 4s will fill first. Right? So that's why I wrote 4s2 first. Now I'm going to write 3d because after 4s, you fill up 3d and then you fill up 4p. So 3d10, 4p, 6, and then we move on to 5s and we're going to stop here. Okay? So 5s, 2. This is the order that you're going to follow in order to fill electrons for any element or an atom of any element. Clear? Okay. Yeah. Now let's write down the rules that you need to follow. Rules for EC. What's EC? EC is electronic configuration. Electronic configuration is the rules that you need to follow. Rules for EC. What's EC? EC is electronic configuration. Electronic configuration is the rules that you need to follow. Rules for EC. What's EC? EC is electronic configuration. Electronic configuration is the rules that you need to follow. Rules for EC. What's EC? EC is electronic configuration. Now there are some rules that you need to follow. The first rule you just studied right now, that electrons will fill in that subshell or orbital first, which is closer to the nucleus because it is more stable. It has low energy, right? So that's the first principle. You call that your Aufbau principle. Now you don't need to memorize the name of the principle or the principle itself, but you need to know how to apply it. Okay, so the Aufbau principle says that electrons will be filled electrons will be filled in the order of increasing energy, starting with the lowest energy orbital. And in order to apply this, you just follow this diagram, because we're starting with the lowest energy orbital and then we're moving toward higher energy, right? So this is the first principle that we need to follow, or for the first rule that we need to know for electronic configuration, and we will apply this very easily. What's the second one? The second one is known as Pauli's exclusion principle. Again, you don't need to know this person or the name of the principle, but you need to know how to apply it. What is Pauli's exclusion principle? Now, this principle states that each atomic orbital or each orbital can hold how many electrons? A single orbital holds how many maximum electrons? Yep. So this basically principle states something we already know, but it also states something that we don't know right now. So each orbital holds a maximum of 2 electrons, but if 2 electrons are present in the same orbital, they must have something. What is that something? They must have opposite spin. Now why should they have opposite spin? Because both of the electrons are charged, and charged species have a magnetic field around them, right? And 2 electrons are both negatively charged, and what do negatively charged species do? Do they repel each other or do they attract each other? Yeah, they repel each other, right? So they need to have opposite spin in order to cancel out each other's magnetic fields, so they have minimum repulsion between them when they're arranged in a single orbital. In order to minimize repulsion, okay, and this type of repulsion, which is in between 2 electrons, it's known as spin pair repulsion. So it's known as spin pair repulsion. So how do you arrange 2 electrons in an orbital? Do you arrange them like this? So the arrow represents an electron, all right? So this is also known as the box notation. Do you arrange them like this, or do you arrange them in opposite directions? Yeah, when you have a pair of electrons in an orbital, they should always be in opposite direction. This is wrong, because this is not a stable arrangement. This is a more stable arrangement on the right hand side. Okay, so one has spin up and the other one has spin down. Let's move on to the third principle. Now this isn't a very hard principle to memorize. Basically, you have to, whenever you write 2 electrons in a single orbital, in box notation you have to show them having opposite spin. The last one is the Hund's rule. Now this rule is important. Out of all of these rules, this one is the most important rule. Now the Hund rule says, whenever you're filling electrons and you have degenerate orbitals, what did you say? What were degenerate orbitals? What were degenerate orbitals? Yep. So in case you have, yeah, in case you have the 2p subshell which has degenerate orbitals, it has px, py, pz which are at the same energy. What does the Hund's rule say about them? It says if you have degenerate orbitals, the electrons won't pair up because pairing has repulsion between them. Because after pairing, they have repulsion between them. So in order to minimize this repulsion, if they have available empty orbitals, they will first occupy them without pairing with each other. But if they're forced to pair, then they will start pairing. Okay, let me explain that further. Let's write this rule. So basically, when filling a subshell, so when filling a subshell which has degenerate orbitals, electrons must first stay unpaired in each orbital. So electrons must be unpaired and they should not be paired initially. They will stay unpaired and they'll occupy every single orbital. Okay, separately. They will not be paired. So electrons must first stay unpaired and and occupy each orbital separately with same spin before pairing up. Because when electrons are paired, there's repulsion. Even if they're oppositely spinning, still there's a bit of repulsion compared to if they're separately occupying different orbitals without pairing. All right. So this is the first rule. Sorry, the third rule that you need to apply in order to write the correct electronic configuration. For example, if you had the 2p orbital and you had to fill in 3 electrons, how would you fill in 3 electrons? Would you do this? Will you pair up the electrons initially when there is an empty orbital present? No, you should not do that. What will you do? You'll keep them with the same spin but unpaired initially. Now if you had to fill 4 electrons, so you fill all the 3 electrons initially, unpairing the electrons. Now the fourth one has no way to go but to pair up with this electron, right? And the fifth one again has to pair up with this electron. So the Hund rule says that if you have empty orbitals and you have to fill electrons in them and those orbitals which are degenerate, so all these 3 orbitals have the same energy. So electrons will fill up these orbitals but they will stay unpaired with same spin unless they're forced to pair up after this. Okay, so what if you had to fill 7 electrons in the d orbital? D can accommodate 10 electrons. First you would fill 5 electrons unpaired with each other. Now you're left with 2. How would you fill those 2? Now they have to pair up, right? So now you'll start pairing them up, 6 and 7. Understood? So you don't pair electrons till you have empty orbitals. You start unpairing them and you keep them with the same spin. You let each electron have its own orbital, but after the empty orbitals have been occupied by every single electron, then you start pairing them. Okay, so 3 rules basically. What was the first rule? That electrons will start filling the orbitals which are closest to the nucleus. first, and then they'll move on to higher energy levels. Second rule, that an orbital can hold a maximum of 2 electrons, but both of those electrons, when they're present in the same orbital, they must have opposite spin in order to minimize their repulsion, because they're both negatively charged. And the third rule, if you have degenerate orbitals, initially you're going to put electrons separately in each orbital, and after that you're going to start pairing them up. Okay? Now let's do electronic configuration. Yeah. Okay, the half-filled and full-filled thing, we're going to move on first. We'll start the electronic configuration, and the moment we have to talk about that half-filled and fully filled stuff, then I'll talk about it. But right now it's too early to talk about it. Okay, we're moving in the sequence right now. So let's write down the electronic configuration now of the first 20 elements. That means you're moving from hydrogen till calcium, starting from proton number 1 and moving on to proton number 20. These are the first 20 elements from hydrogen till calcium. Now, before starting electronic configuration, for initially what you need to do is just make this quick diagram with me. So 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, and 4s. Then 5s, 5p, 5d, 5s. Okay, just for your help, if you get stuck initially, then you have to just draw this. It'll take just 3 seconds and you'll have the proper order with you. Let's start with hydrogen. Hydrogen is H11. So how many electrons would hydrogen neutral atom have? It has 1 proton, so it has 1 electron. Right now we're going to do the 1s notation. That means you write the subshell and you write the electrons in its exponent or power or superscript. Yep. So it has 1 electron. So where would you go first? You go to the first subshell 1s, and can 1s take this 1 electron? Yep. So 1s1 is the electronic configuration for hydrogen. It has 1 electron in the s orbital. Let's move on to helium, He24. How many electrons does helium have? It has 2 electrons. So first you go to 1s. Can 1s take both these electrons? Yes. So 1s2. Right? So let's move on to lithium, Li37. 3 electrons. How would you fill these 3 electrons? Now you have 3 electrons. First you go to 1s. Can 1s take all 3 electrons? No. It will just take 2. No, thank you. And then where will the next electron move on to? After 1s, where do you fill? 2s. Yep. So 2s, can it take the remaining 1 electrons? Yep. So 1s2, 2s1 is the electronic configuration for lithium. Now you move on to beryllium, Be49. So it has about 4 electrons. How would you write the electronic configuration? That would be 1s2. Then you move on to 2s. Can 2s take both the remaining electrons? It can. Right? So what about boron, B511? It has 5 electrons. What would be the electronic configuration? 1s2, 2s2, and then 2p. Yeah, very good. So after 2s, you move on to 2p, and you do not move further unless 2p is fully filled, which means it has 6 electrons. Right? So right now you're left with 1 more electron that you have to fill. So you move on to 2p, and 2p can easily take this 1 electron. Right? So what about carbon? Carbon has 6 electrons. It would be 1s2, 2s2, and 2p, 2. What about nitrogen? Nitrogen has 7 electrons. 1s2, 2s2, 2p. Should I move further? Because 2p has 2 electrons now. Yep, it can not only accommodate 2, 3, 4, 5, it can accommodate a total of 6 electrons. You do not move on unless P has 6 electrons, right? So 2p3. What about oxygen O816? It has 8 electrons. So 1s2, 2s2, 2p, 3, and then you move on to 3s1. Yep, 2p4. P is still not filled yet. Okay, then F919 you have fluorine, 9 electrons. So 1s2, 2s2, 2p, 5. Then you have neon, 1020. That's 10 electrons. So 1s2, 2s2, 2p, 6. Yep. And what about sodium 1123? So it would be 1s2, 2s2, 2p7, right? Exactly. 2p was filled. After these 6 electrons, 2p had no more space. So the next electron goes into, after 2p you fill up 3s. So 3s1. So what about magnesium 1224? It has 12 electrons. So 1s2, 2s2, 2p6, 3s, 2. Yep. What about aluminium 1327? 13 electrons. So 1s2, 2s2, 2p6, 3s3, right? No. The s orbital could only accommodate 2 of these electrons. After 3s, you have to move forward. What comes after 3s? 3p. Yep, so 3p1. What about silicon? 1428. Then phosphorus P1531. Then you have sulfur S1632. And then you have chlorine 1735.5. Then you have argon 1840. Then you have potassium 1939. And then you have calcium 2040. Okay, start from here, from silicon. Yeah. Hmm. Yep. So 1s2, 2s2, 2p6, 3s2, 3p2. What about the next one? 15. So it would be the same, but in 3p you would have one more electron, right? 3p3. The next one would be the same, but in 3p you would have 4 electrons. And about chlorine, same electronic configuration. 3p you'd have 5 electrons. And in argon, 18 electrons. So 1s2, 2s2, 2p6, 3s2, 3p, 6. What about potassium? 19 electrons. So 1s2, 2s2, 2p6. You're done with 10 electrons. 6 to 2. That's 10. We're left with 9 more electrons. So after 2p, you move on to 3s. So 3s2. Now you're done with 12 electrons. Then you move on to 3p. So 3p6. How many are you done with now? So 6 plus 2 plus 2. This is 10. And then plus 8. So we're done with 18. Where does the next electron go? 3p is completely filled. After 3p, you fill electrons in 3d, right? Yeah, exactly. 4s is closer to the nucleus, so you fill up 4s first. So the next electron goes into, the last electron goes into 4s. Now what about calcium? 20 electrons, so it would be the same. After 3p6, you'll fill up 4s2. Okay?